Hi everyone, my name's Tom Pritchard and with me today is Matthew Gilbert, who's our main speaker. Today we're going to be discussing how you can reveal and utilise hidden strength in reinforced concrete slabs, and more specifically how you can achieve this by taking advantage of the yield line method and LimitState SLAB, our automated yield line analysis software. The presentation itself is due to last about 35 minutes, and there should be 5 or 10 minutes at the end where you can ask questions. You can post these at any time using the question panel that should be present in the webinar interface and that you should have on your screens. If you do have any questions about the software after the event has finished, then you're always welcome to contact us outside of the webinar via info@limitstate.com or by telephoning us during UK office hours, and we'll be more than happy to speak to you in detail. So without further delay, I'm going to pass you on to Matthew Gilbert, who will be speaking to you about the approach we took to automating yield line analysis.
Thanks very much, Tom, and thanks very much everyone for joining us for the webinar today. Okay, so the first slide up, it just shows you contrast of the typical textbook failure mechanisms for yield line patterns that you'll see on the left, and then the more complex and arguably more realistic geometries that you might be faced with when you are going about your day-to-day business as a structural engineer. So left-hand side ones, simple, classic yield line patterns. The right-hand side ones, much more complex due to the more unusual boundary conditions and the potential presence of holes. And the next slide just shows what the modes of deformation are in these different cases. So what we're going to be doing today is looking at how we can set up and solve yield line analysis or design problems, whatever the geometry that you might be faced with. In terms of the breakdown of the webinar, I'll say a few words about LimitState, then jump in and provide a bit of background to the yield line method for those of you who are not familiar with it, then have a quick software demonstration before talking about how it works, and then look at how we validated that against a number of examples, some academic, some real world. And then Tom will be back in the chair and will provide you with a software demonstration of how you can actually set up and solve various problems. And we'll wrap up with conclusions and then questions. Okay, so first just a few words about LimitState. We were set up actually more than 10 years ago now, in 2006, to provide engineers with powerful software tools, primarily for the ultimate limit state conditions, whether that be analysis or design. We take advantage of optimization tools, which commonly available software programs in the marketplace don't, and we provide software which is robust, well validated and easy to use, and a number of our customers for this product shown on the right hand side. In terms of where our focus is in the sort of the great landscape of analysis software programs, we sit somewhere in the middle effectively. So traditional hand calculation methods often result in simple software programs or might be embedded in a spreadsheet. Those are nice in that they can get solutions very quickly. The downside is that they can only deal with a limited number of, for example, failure mechanism typologies. At the other extreme, advanced methods based on, for example, non-linear finite elements, discrete elements, and a whole plethora of other tools. Very powerful, very flexible. A downside is they need lots of operator expertise and often lots of runtime. So what we're trying to do with our LimitState products is effectively get the best of both using numerical, rigid plastic or limit analysis techniques. So best of both in the sense of you don't need huge amount of operator expertise to use the software, and you can get solutions very rapidly. Also, you can set up real-world geometrical configurations in a way that you can't with traditional hand calculation type methods. Okay, so focus of today is on the yield line method, in particular the automated yield line method. But first of all, just take you back to the traditional hand yield line method. How do we apply it? What is it? Basically, it's a direct analysis tool where we're looking at the slab simply at the point of collapse. So what we do typically is we guess a yield line pattern, so the geometry of the yield line pattern. We then equate internal and an external work to determine the collapse load factor, or in a design context, the moment capacity needed to deliver the required capacity. So pretty simple calculations. That's the clear benefit of it. Another key benefit is that you tend to obtain much more economical designs than if you use elastic methods, or in an assessment context, you can reveal hidden strengths of capacity in the existing slab. The downside is, if you're working with a hand method, it's unconservative if you choose the wrong mechanism. So if you miss that critical failure mechanism, you're going to overestimate the true collapse load. That is a key area that we're able to address with the automated method. We take the guesswork out of the process effectively. Second con, which we don't seek to address, is that it does only consider flexural failure. So punching shear failure, for example, is not explicitly considered, and deflections under service load, for example, is another area which is not covered by the yield line method. In terms of application, this is some years old now, but in the 90s and 2000s, Middleton and co-workers at Cambridge used the yield line method very effectively to demonstrate that many UK bridges had hidden reserves of strength. So what they did was they compared the elastic assessed capacity, shown by a red bar, with the plastic assessed capacity, shown by the green bar, for a population of bridges, in this case 21 bridges. And they found in the great majority of cases that bridges that had been identified as being substandard using elastic methods were actually perfectly adequate when plastic methods, i.e. the yield line method, was applied. How did they do that? Well, they had quite a neat tool where the software could go through a series of potential yield line patterns. You can see actually a library of yield line patterns, 27, shown on the right hand side, and it would basically go through those and identify which of those gave the lowest assessed capacity. So pretty nice. The downside is, what if there's a mechanism number 28, number 29, number 30, which is not listed on the internal library of collapse mechanisms, which is actually critical in the case of the bridge that you're faced with. So useful, but there's a danger still that you might miss the critical yield line pattern. If you think about application to buildings, about the same time, Carlington European Building Project, part of their work focused on different design methods for concrete slabs, and it concluded that the yield line method led to highly economical slabs, and also slabs which were pretty simple in terms of the number of bar marks, number of different configurations of bars that needed to be designed. So it was a nice mix of economy and simplicity. If you've got an existing building, you might find that the yield line method, the automated yield line method, can identify hidden reserves of strength. If it does, expensive strengthening work can be avoided. One of the things about concrete buildings is It tends to be very expensive when you come to strengthening. And the other thing to say is often building floor plates are a bit more complex compared to bridge decks, so it's less likely that we could replicate the method that Middleton proposed for identifying a sort of a range of 20 or 30 different patterns. The other thing to say is if you're dealing with a existing structure, then potentially you can deal with the serviceability requirements via simple load testing. So you could actually check that the building satisfies those constraints that you might be working with, for example, by filling up water tanks and exerting load that way. What I'm going to do is, it's been a little bit abstract, is just start the software and just show you very quickly how we can set up and solve a very simple problem, and then Tom will come in and solve some slightly more complex problems. So when you start the software, you can set up a new project. I'm going to set up an empty project, so it's actually no geometry or anything associated with that. I'm simply setting up what the workspace is going to look like in terms of the limits of the grid and so forth. And actually, I'm going to just use the defaults for this because it's just a quick way of demonstrating how the software works. So, split into a number of regions. There are a number of toolbars. The blue tools are related to geometry functions. So, for example, what I can do is I can use a polygon function to actually draw just in freehand using the grid that's given to actually draw the geometry of a slab. And I'll choose an irregular geometry just because it's probably better for illustrating the power of the method. So I've got a polygon now, and I've used these construction lines as a guide. I'll turn those off now, and so we've just got the slab geometry of given dimensions. What I'm going to need to do is set up some supports, so I can select the external boundaries and I can choose whether I have symmetrical, fixed, simple or partially fixed boundaries. I'll just choose simple supports for sake of simplicity, excuse the pun. I then need to apply some load, and I can select the whole of the domain and provide a pressure load. I'll just provide a unit pressure in this case, just for simplicity. So now I've got a slab with geometry as shown and load. The last thing I need to do is apply a slab material definition. So what I'm actually going to do is I'm going to use one of the inbuilt ones, the unit MP, that's plastic moment of resistance. Just drag that onto the domain, as you can see. Now, clearly in reality, it'd be more likely that you would spend some time setting up the given parameters that are appropriate for your particular slab. But I've got enough now to simply solve the problem and let the software identify the critical yield line pattern. So you can see that in a matter of a couple of seconds, we're able to identify the critical yield line pattern and also the adequacy factor on the applied load. Now this is a little bit abstract because we had a unit MP value and also a unit pressure load, but normally if you've got factored plastic moment of resistance and factored loads, then the adequacy factor would be effectively an over-designed factor or a sort of overall safety factor that you'd want to be 1 or greater. In this particular case, it's just saying that I can effectively multiply the pressure load by 7 in order to cause collapse. Because the software is so quick and easy to use, I can very readily change support. So for example, I can change a couple of the simple supports to be simple, and you can see that I get a similar but slightly different mechanism, and the adequacy factor falls from 7.2 down to 6.97. And perhaps if I a bit more radical, take away a couple more supports, we'll see a bigger drop off in that adequacy factor. And so you can see this is exactly what's happened. It's now gone from the order of 6.9 or 7 down to 2, and we've got a much simpler failure mechanism. So this kind of indicates how quickly and easy it is to identify a critical yield line pattern and associated margin of safety using the automated method. So question is, how does it work? Well, we use something called discontinuity layout optimization, or DLO for short, which is a quick and direct means of identifying the critical yield line pattern. This work was published in Proceedings of the Royal Society Journal in 2014, so 5 years ago. And what we were able to show is that unlike the suggestion of some previous workers, you could actually boil this down to a simple linear optimization problem. What does the process look like? Well, first of all, we start off with our slab. We populate the slab with nodes. We connect each node to every other node with a potential yield line. And then we use optimization to identify the critical minimum energy solution. So in this particular case, you can see the yield line pattern indicated by the red and blue yield lines, hogging and sagging respectively. In terms of the mathematics, this is basically all there is to it. You minimize the energy subject to compatibility constraints and a unit displacement constraint according to the principle of virtual work. The main constraint of interest is a nodal compatibility constraint, which I can show again here. And basically what we're saying is that if we zoom in on a particular node, that if we resolve the rotations in the x direction and in the y direction, as we go round the node and come back to the starting point, those must sum to 0. It's very much akin to force equilibrium in a truss. So in a truss, we would typically resolve forces in the x direction, they must sum to 0. Resolve forces in the y direction, they must sum to 0. It's the same here, but now we're resolving yield line rotations. And this, if you're interested, there's actually a more accessible explanation of the theory in a paper published in the Structural Engineer in October 2015. So I'll show a few examples, and then Tom will dive in and show some more in-depth usage of the software. So this slide just shows a simple square slab with a couple of changes. The first two on the left-hand side have got pressure loading. So the left-hand side slab has got a simple support. The middle slab has got fixed support. What we're able to do with the automated method is automatically identify these more complex yield line patterns, such as fans, whether they occur at the corner or in the whole of the slab. The right hand slab is the same as the middle, except for now we've got a point load at the centre of the slab as opposed to a distributed load. So for all these problems, we're able to get solutions within a very small fraction of 1%. But of course, because this is now general, we can deal with more complex slabs. So for example, here we've got a slab that's in the literature where we've got some quite asymmetrical boundary conditions, slab geometry as well, and also a hole. And basically, for all the problems we've tried, we've found that DLO gives a better solution than any other proposed in the literature. And then the last example I'm going to show is actually a floor plate for an apartment block that was constructed in central London. And this is actually the same apartment block that was considered in the Concrete Centre guide from around 15 years ago. So what they did in that design guide is they used a hand-based yield line method. And what they basically did was try lots of different potential yield line patterns in order to identify the critical one and then design on that basis. And you can see that one of the mechanisms is a kind of folding plate mechanism where we've got effectively a fold from one side of the building to the other. And that's what was found to be one of the most critical mechanisms. And when we entered the details of the geometry into LimitState slab, we actually found that that wasn't far off the mark. And actually we were, I think, less than 10% lower than the automated yield line method solution. The main difference, though, is this literally took, well, a few minutes to set up the problem and then a few seconds to solve, whereas those hand-based yield line analyses each took considerably longer than that. The other thing is here we can have much more confidence that we are identifying the critical yield line pattern because of the vast numbers of potential mechanisms that a modern computer can churn through effectively in a short space of time. Okay, so that's all I wanted to say. I'm going to hand you over now to back over to Tom, who's going to provide you with a demonstration of more of the software's capabilities.
Thanks, Matthew. So like Matthew says, I'm just going to take you through a few more of the capabilities of the software itself, split it into 3 parts. So we'll look at the software interface in a little bit more detail, and then talk about the wizards and the general usage, and then moving on again to an apartment block example, but looking at more complex geometries. Excuse me. So if I open up the software again, so first thing we're going to look at is a little bit to do with the interface. So Matthew's already mentioned the geometry buttons on the left hand side. I'll just take a wizard and open up everything. So we've got the geometry buttons here on the left hand side. We also have a number of different features, especially the purple buttons at the top here, which allow us to delve into loading and load cases. So what we can do, I won't do it here, but I'll sort of explain it, is that you can apply self-weight loads, pressure loads, and also line loads and point loads, which come in very handy if you're looking at walls or if you're actually trying to model moving loads. For instance, if you have a bridge or something like that and you have a slab that you wish to analyse there, then you can move point loads across as if it was a vehicle or something like that. You can set your own loads and also set your own partial safety factors. And then possibly the most important part of the software interface is the right hand side here, which is the property editor, and you'll have seen Matthew using that quite a lot during his demonstrations. And effectively anything that we select within the window here will be reflected in the property editor. So here I've selected this solid, and you can see all the properties of that solid are then displayed on the right hand side here, and you can modify them as necessary. So in this case we can change the nodal spacing if we wanted a tighter or a looser grid on there, or if we wanted to change the material that we're applying to it, we can do that here, although I'm going to keep this on the unit MP weightless. if I just solve this problem, so it's the one that I set up through the wizard, so it's going to have unit loading applied to it. If I turn on the display of load, you can see here it's got a unit pressure load and fixed supports around the edges. If I solve it, what you'll have already seen is the software going through the potential failure mechanisms and homing in on the optimum solution, but also you've got this representation of the critical yield line that you can animate and see in more detail how the slab is failing, as well as where these yield lines are. But also, if we go to analysis and click report, what we can do is generate a report output that you can then use yourself or give to other people, with various different sections within it. You can see here there's a summary. It tells you what the adequacy factor is. It also tells you what the critical failure mechanism is, and also provides information about the different aspects of the setup of the problem. So things like which structural definition you've used, what the partial safety factors are, what the loading is, etc. So what we're going to do now is move on to look at a little bit more about the wizards and the general usage. So we've already had a quick look at this, but I will go back and start a new one. You can see when we start a new project, you have the option to use an empty project like Matthew did, where you just set up the grid and draw things freehand. You also have the option to set up a rectangular slab either with or without a hole. In our case, what I'm going to do is just click a rectangular slab without a hole. Don't need to worry too much about the project details, but in the geometry, what I'm going to do is, instead of having fixed supports around the edges, I'm going to set them all to simple. I'm going to keep the dimensions the same, and then go through. We have structural definition, so you can actually create your own or use one of the built-in ones. Again, in this case, I'm just going to keep using the unit MP weightless structural definition. And here we have load cases. Again, if we look at this, we can see that what we're doing is we're allowing self-weight to exist, but actually we've not worried about that in our structural definition. But what we are worried about are the pressure loads, where we said we're going to have a unit pressure and it's unfavourable. And this column here, we're saying adequacy true, is basically that is the load that we are going to increase in order to drive collapse. So the factor that we get out as the adequacy factor will include the concept of this being increased in order to drive that collapse. And the last thing before we solve is the analysis options, and you can see here you can change the nodal density. So as Matthew was explaining how the DLO method works, obviously the more nodes that you put into the problem, the finer the collapse mechanism it will be able to find is, but then obviously there's a slight trade-off in there in terms of computation. So what we normally do is keep it on medium, and if I click finish here, we can see we have our problem already set up. If I click solve, it goes through the analysis and we get quite a standard envelope shaped failure mechanism for this one. But what we might want to do is, and as Matthew alluded to, is we can do what if type analysis very quickly. We say, okay, we have this, what if we are wanting to use a material where it's orthotropic rather than isotropic. So if I create a new structural definition, and in this case the first direction I'm going to have my positive MP value as being 5 instead of 1, click OK, and I just drag that on there, replace the one that's already in there, and click solve. What we can see is, again, very, very quickly, the software identifies a different failure mechanism based on the different material properties that we've got in there. So obviously the central sort of horizontal part of this envelope failure mechanism is extended because of the higher value of MP that we've got in that position. So what I'll do now is actually I'll take it back to 1 and unlock, solve again. You can see now we've gone back to the original envelope type failure mechanism. The next thing we might want to do is consider what happens if we have a column somewhere in the centre of this slab. So if I just select a rectangle, all I need to do is zoom into the middle and draw a square like that, and then if I delete the middle of it and set the boundaries around the edges, in this case to be fixed, then essentially that's saying we have a column in the centre of our slab or slightly off centre, and we can see what the effect of that is. So again, the solution process is very, very quick. It only takes a matter of seconds, and we can see actually it's quite an interesting combination of an envelope type failure mechanism, plus around where this column is we've got this fan or bicycle wheel type failure pattern in that area. And what we can also see is that the adequacy factor has gone up from just under 1 in the original case to 2.26, so we've more than doubled the capacity of the slab just by adding this column into the centre of it. Another thing we might want to do is look at the repercussions of taking away the support from the right hand side here, so that's what I've just done. You can see again all you do is select the boundaries in question, and you can change the support type between free, symmetry, fixed, as we mentioned earlier. If I solve, you see actually we've got quite a dramatic change in failure mechanism here. So instead of having the fan around the column and that envelope type failure mechanism, the combination of those two, what we've got here is basically just the sort of cantilever failure towards that right hand side where the free edge is now. So it's not actually taking into account much to do with the column apart from the fact that it's providing some restraint there. But yes, again, the adequacy factor has gone down from 2.2 to 1.1, so effectively halved the capacity of the slab by removing the support of that right hand side. So maybe in this type of situation we want to see, okay, we've taken that support away, but we actually, if we add a column in on that right hand side, what's the effect of that going to be? So again, all we need to do in this particular case is take away where the column is and fix around the edges. So again, if we put fixed in there, you see now we've got two columns, one slightly off centre and one on the right hand side where those free edges are, and if we solve, you see we get again quite an interesting failure pattern. So we've got this circular fan mechanism around the central column again, this envelope type failure mechanism, and then also a sort of half circle around the right hand column. And in this case the adequacy factor has gone back up again to 2.3, so we've gone from 1.1, 1.2 up to 2.3, so again roughly doubling the capacity of that structure by adding this column into the right hand side. So the last thing we're going to have a quick look at is how we can deal with slightly more complex geometries, because at the moment we've looked at things that are quite simple, and how we deal with that in LimitState Slab is to import a geometry from DXF. So if there you can see here actually we've got an apartment block floor that has already been defined in DXF, and if I click open we have a dialog that gives us some of the information about that file. So we can see that the extents of it, so the maximum x and y, and also how many layers there are in there, and we can actually select layers or deselect layers to import as necessary. If I click OK, what we can see is that the DXF has been read in, and what the software does is that it takes closed loops within the DXF file itself, so where the lines form closed loops, and it interprets them as solid zones. So immediately you've got a geometry that you can select and assign structural definitions or loading or support to. And that's what we're going to do in this case. So we have our floor slab defined, but what we might want to do is also read in some materials, and if I right click in the structural definition explorer here, we can import the structural definitions from a CSV file. So we can see here I've chosen that CSV and it says 7 definitions have been imported, and then on the left hand side here you can see that they've all been read in, and then all we need to do is assign those to the relevant parts of our geometry. So the main floor, if I want parts of this to be main floor, we can do that very readily. If I want parts of it to be balcony, I can do that. And similarly you can do that for all the different zones within the problem. The last thing we would need to do is then go around and find the parts where we need to provide support, and in this case we have areas where we want columns to exist because there aren't actually going to be any wall support, it's all going to be via columns, so we would just treat that in the same way as we did in the last example and just delete the squares and select the boundaries, set them. In this case we have them as simple. We will go through and just select all of the columns that we want to do, and you can hold down Control and select multiple columns and assign the boundary conditions for those. And then the last thing we would want to do is apply some loading, and we can do that through the load case manager. And if we click in the loads database, what we would do is add our own loading types in there. So in this case, if we have different loading, say in the main floor and the stairs and the kitchen, we would just click in there and say okay, for the kitchen maybe we're looking at 11 kilonewtons per meter squared, and that would be a permanent load, and we click OK, and you go through and do that for each of the different areas. And then once you've got to that point, what you can do is then assign that as a pressure load to the different sections that you want. So maybe I want that to be a kitchen, click OK. Obviously we would have the structural definition in there as well, but then that means that A, we've got kitchen structural definition, and B, we've also got pressure loading in that area. So you can very quickly build up a problem that's quite complex just using a combination of DXF file and predefined structural definition properties from a CSV file. So what I'm going to do is I will just open that problem and we can go through and solve it. And you can see within a matter of 2 or 3 seconds what's happened is that the software has identified the critical failure mechanism for this particular problem, and it's involving a large sort of chunk of the main floor, where we know if we click on here that the loading is over the largest area, and we know proportionally speaking it's going to be the sort of the heaviestly loaded part of the structure with the longest span, so it's not inconceivable that that's where the critical failure mechanism would be. And then there's also some slight areas at the top as well where the failure mechanism extends to, but the main part of the failure mechanism is in that main floor part there. And we can see also that the adequacy factor is just in excess of 1, so as long as we have partial safety factors applied in there, then a value of adequacy factor above 1 is going to say that this solution is okay for that particular scenario. So we've had a look very quickly at the interface. We've also looked at the wizards and general usage and how you can very rapidly ask what-if questions and get solutions to that. And we've also seen how you can import geometry from DXF files and import materials and structural definitions from CSV. And so hopefully that's given you a good but a very quick overview of how the software works and how it can identify these critical failure mechanisms that you may not be able to realise using hand-based methods. So if we go back to the demo, come to some conclusions. So hopefully what we've seen is that the software is automating the yield line analysis method in a way that allows you to very rapidly get solutions that you couldn't get, like we say, by hand. So what we can do now is just open it up for any questions that people may have. So if you have anything, then please feel free to type it into the question interface in front of you, and we'll try and get around to that for you. Okay, so we've got one question just saying, if the slab has different thicknesses and strengths in different areas, how can we deal with this? So yeah, so that's something that we didn't really touch on during the webinar, but what I can do is hopefully show you in here. So I'll make a new problem. So here we've got a single solid zone, what we can do is maybe split that up into 2. So now we've got 2 areas, and all you need to do is have a new structural definition for each of the different areas. So we can see here structural definition 1, and just for the sake of this I'm going to make them vastly different colours, so I'm going to make it green, and we'll say okay, that's 10 in both those directions, and maybe 3 in that direction, and then we'll make another new structural definition and make that one purple, and instead of that 10 and 3 we can have 5 and 1 in each of the directions. And then all you would do is drag and drop these onto your problem as necessary. One thing we didn't actually look at there though was the thickness here. You can actually set the thickness and the unit weight for each of these different materials or structural definitions individually. So if you had areas, maybe you've got like a waffle slab or something like that, where some parts of it are a lot thicker than others, then you can set the thickness and the unit weight of those as necessary. Okay, we've got another quick question, probably time for one more. So the question is, can you consider uplifting it? I think maybe some people had seen very briefly as we were going through that there may have been the option to do that, so the answer is obviously yes. So what we'll do here is we'll have a quick look at this. If we have simple supports here, we can see that without the presence of uplift, then around the edges the slab stays where the supports are. But with this simple support model, what we can actually do is, if we select these boundaries again, we can see here in the property editor that the option to have support lift off is there. Currently it's false. If I set that to true and then solve again, what we'll hopefully see, as well as a change in the adequacy factor, so it's gone down from 1.22 to 1.13. We can also see around the edges, especially in these corners here, that we're actually getting lift off of the slab vertically away from the supports there. So yes, you can include uplift off the supports as part of the analysis. Okay, so I think that's probably about time for everything today, so I'd just like to say thank you to Matthew and thanks to everybody for listening. We do hope that you found the webinar informative, and as I mentioned at the start, if it has raised any questions that we haven't answered during the course of the proceedings, then please do get in touch via telephone or info@LimitState.com, and we will be more than happy to answer these questions for you. There'll be a recording of this available within the next 24 hours, and you'll be sent a link to it, so you're welcome to share that with any interested colleagues or watch this back again. And I'd just like to also make you aware that LimitState Slabs are available to download or purchase from our website, but we're also currently running a promotion where new purchasers for LimitState Slab will receive a 20% discount up to the end of May. So if it is something that you're considering, then please do get in contact with us about it, and hopefully we can sort you out with that. Also, lastly, just please do look out for our other webinars that deal with both LimitState Slab and all of our other software products, and we do send out event notifications in advance of these through social media and email. So once again, I'd just like to say thank you all for listening, and we do hope that you can join us again for one of the future sessions. Goodbye.